So in this lecture we continue our discussion for the metric topology. Recall from the last lecture that we defined what is a metric function D, which we denoted D, on a set X, and this metric function gave us a basis which we denoted BD, which was the collection of all the sets of the form BDXR. So these were the R balls centered at X, where X ranges over X and R is greater than 0. So our collection BD was a basis, forms a basis. So now that we have a basis, it generates a topology, and this is what is the metric topology. So our definition for the metric topology is just this is the topology generated by this basis by BD is called the metric topology on X. Metric topology on X, and it is denoted as tau D. So tau D is the topology generated by the basis BD. Now let us see some examples of metric functions and the topology that they induce. So the first example we have, is that if let X be any set, and define the function D from X cross X to this positive real line as follows. So dxy is equal to 1 if X not equal to Y, and 0 if X is equal to Y. So it is easy to check. So check that D is a metric function on X. So this I leave it to you as an exercise to check. And so you have to check that dxy is 0 whenever if and only if X is equal to Y. Then you should have dxy equal to dyx, and then you also have to show that the triangle inequality holds, right? So assuming that D is a metric function, it induces the metric topology tau D on X, and I claim that tau D is nothing but the discrete topology on X. So let us see a quick proof of this claim. Okay, so to prove this claim, we simply note that if we choose any X in X and R to be less than 1, of course R is positive and it is less than 1, then the set BDXR, which was nothing but the set of all Y in X, says that dxy is less than R. This is nothing but so R is less than 1, but your metric D takes values, the only values that it takes is 0 and 1. So if dxy is less than R, then the only possibility for Y is X equal to Y. Therefore this BDXR is nothing but the singleton set X. Okay, so this is because all the other points Y in X have a distance 1 from X, right? So if R is chosen less than 1, then the only point within that distance is x itself, which has distance 0. So we see that the basis set for the metric topology is the basis for the discrete topology. This is the basis element for the discrete topology, and so these two topologies are equal. Now let us see another example which we have already seen. So take x equal the real line, and a d of xy is just the usual distance between the two real numbers, which is the modulus of the difference x minus y. So I asked you to show that this is a metric function, on R, and let tau d denote the metric topology on R. Now I claim that tau d is nothing but the standard topology on R that we have already seen. So you might have noticed that whenever we are introducing a new concept, a new definition, then we want to relate it to the previous concepts that we have seen. So here for the metric topology, we are trying to see what we have. We are trying to compare what we have already seen with respect to the different topologies. And for the first one, it was the discrete topology, and this one is the standard topology. So, so why is it the standard topology? So the proof is again quite simple. So if A is less than B in R, A B in R, then what we have is that the basis for the standard topology, which is the open interval AB, this can be written as BD of x R, where x is the midpoint A plus B by 2 and R is the difference A minus B by 2. So what is happening here is you are taking the open interval AB and you want a center x. So the center is just the midpoint A plus B by 2, and the radius is A minus B by 2, which is simply this distance. So this is A plus B by 2 minus A, and this is exactly this should be B minus A by 2, not A minus B. This is B minus A by 2. So here we get B minus A by 2. Similarly, this distance is also B minus A by 2. Okay. So so the basis for the standard topology is precisely of this form, and conversely BDXR given any x and r is equal to the open interval x minus r and x plus r. Okay, so this is the basis in the standard topology is a basis in the metric topology, and vice versa. A basis in the metric topology is a basis in the standard topology. So this implies that tau d is equal to tau standard. Now yet another example is when x is the Cartesian product of n copies of R. So this is R cross R n times. So this is n copies of R here, n times Cartesian product, and here we define the distance, the metric function d from x cross x to the positive real line is defined as follows. So dx comma y is equal to, so here note that x and y are in Rn, then x is of the form x1, x2 up to xn, so these are the coordinates in the Cartesian product, and similarly y can be written as y1, y2 up to yn. And so we define our distance between x and y to be the following expression. So this is x1 minus y1 whole squared plus x2 minus y2 whole squared plus xn minus yn whole squared whole and the entire thing is under the square root. So this is called the Euclidean metric, Euclidean distance function or Euclidean metric on Rn. So we still have to check that this function d is a metric function. So our claim is that d is a metric function on Rn. So the proof is slightly non-trivial, and I will give the steps one by one. So for this proof there is some algebra involved, and we will define some operations on Rn which will help with our proof. So we begin with the following definitions. So define the Euclidean norm on Rn as follows. So if for x a point in Rn of the form x equals x1, x2 up to xn, we define the Euclidean norm, which is written with two vertical bars like this, and this is nothing but the distance of x from the 0 in Rn. So here this is not the real number 0, but this 0 is rather having zeros in all coordinates. Okay, so let me write it 0 bar. So what is this? So this is nothing but the sum of all the squares, x1 square, x2 square, xn square, and there is a square root sign. So if you think of R2, then any point x has the distance, the straight line distance from the origin 0, 0. So this is xy, say. Then the norm of this point, capital X, is just this distance from the origin, the straight line distance. So we will use this norm to prove the fact that our metric function is our function d is a metric function on Rn. Now we also define some operations. Define the following operations on Rn. Operations on Rn. So if x and y are in Rn and c is a real number, then we define the following operations. So first is the addition of two points in Rn, and this is nothing but, so again here x and y are of the form x1, x2, xn, y is y1, y2, yn, and so x plus y is nothing but the element wise sums. Okay, so this is x1 plus y1, x2 plus y2, coordinate wise sums of the vectors x and y. Similarly, we define c times x, and this is nothing but the coordinate wise multiplication by c. So now this is just the usual multiplication in Rn, in R, multiplication in R. Similarly, this is addition in R for each coordinate, right? And here you have cxn. And finally, we define the dot product. So this is the dot product of two points in Rn, and this is nothing but the sum I equal to 1 to n xi yi. So this is x1 y1 plus x2 y2 plus xn yn. So it just means that you are multiplying the first coordinate of x with the first coordinate of y, the second coordinate of x and with the second coordinate of y, and so on, and adding them all up. So you might recognize this as a generalized dot product from the usual dot product in R3, for example. So we have these three operations that we will use, and a first exercise to show that if x, y and z belong to Rn, then we have the following distributive property of the dot product, which is x dot y plus z is equal to x dot y plus x dot z. So this is the distributive property of the dot product. So we will use this distributive property as well. And the second property that one can show is that the Euclidean norm squared is nothing but x dot x. So this is also quite easy, and I leave it to you. Now we will prove what is called the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality, which is the statement that if x, y are in Rn, then x dot y is less than or equal to the Euclidean norm of x times the Euclidean norm of y. So now x dot y is a real number, and the Euclidean norm of x is a real number, and Euclidean norm of y is a real number. So this inequality is in the real numbers. So we will try to show this. So let us try to prove this Cauchy-Schwarz inequality. So first thing to note is that if a and b are real numbers, then the norm of ax minus by is always greater than or equal to 0, just by the definition of the Euclidean norm. Okay. Now using the second property here, so then we have ax minus by squared. This is equal to ax minus by dot ax minus by. And now if you expand this using the distributive property and also the scalar multiplication and addition property, then what you get is the following expression, which is a square x dot x minus 2ab x dot y plus b square y dot y. So here you have to use that ax dot by equals ab x dot y. That's one thing. And also that x dot y is equal to y dot x. So we use these two properties here. And now what we are going to do is to just plug in some particular values of a and b to get our Cauchy-Schwarz inequality. So now take a equals 1 over Euclidean norm of x, b equals 1 over Euclidean norm of y, and here we have to assume that x and y are non-zero vectors, because otherwise the Euclidean norm is 0 and then a and b are not defined. But notice that if the Euclidean norms are 0, then x and y are if x and y are 0, then the Euclidean norms are 0, and then the dot product is also 0. So the Cauchy-Schwarz inequality just says 0 less than or equal to 0, and this is trivial. So we can assume that x and y are non-zero vectors, and now what we get is ax minus by squared is positive. This is equivalent to a square x dot x minus 2ab x dot y plus b square y dot y greater than or equal to 0. And now if you plug in the value of a and b here, what you will get is that this will be 1, this will be 1, and this term will give you, so let me write it. So 1 minus 2x dot y over norm of x times norm of y plus 1, this is greater than or equal to 0. And now you can rearrange this, and after some rearrangement you will get the Cauchy-Schwarz inequality. Okay, so this is the Cauchy-Schwarz inequality. So this was the first step for proving that D is a metric function. The next step is to show that the norm of x plus y is less than or equal to norm of x plus norm of y. So here again we can use the fact that the norm of x plus y whole squared is equal to x plus y dot x plus y, and if you expand this, you will get x dot x plus 2 times x dot y plus y dot y, and this is nothing but norm of x whole square, this is nothing but norm of y whole square, and here this is less than or equal to norm of x times norm of y by the Cauchy-Schwarz inequality. So what you get is that this is less than or equal to norm of x plus norm of y whole squared, and now this is equivalent to say that norm of x plus y is less than or equal to plus norm of x plus norm of y. And now we can finish the proof of the fact that D is a metric function. D is a metric function using these inequalities. So the only non-trivial part is the triangle inequality. So I leave you to check that dxy equal to 0 is if and only if x equal to y, and dxy equals dyx. So these two things are easy, and I leave it to you as an exercise. So the only non-trivial part is the triangle inequality. And for the triangle inequality we take 3 points x, y and z belonging to Rn, and then dxy, this is nothing but the Euclidean norm of the difference x minus y. This is by the definition. And so now we can, what you can do is take the point z and add it and subtract it. So we take x minus z minus y minus z. Okay, so we can check that this gives you the same vector x minus y. And now we can use the triangle. So this is the triangle inequality for Euclidean norm. Triangle inequality for the norm. And now we can use here the triangle inequality for the norm, which gives us norm of x minus z plus norm of minus y minus z. Okay, but the norm of minus x is equal to the norm of x. Okay, so we can use that. So what we have is norm of x minus z plus norm of y minus z. Okay, since norm of minus let me call it s, any vector s is equal to norm of s for any s in Rn. And now this is nothing but the distance between x and z, and this is nothing but the distance between y and z. Okay, so then the triangle inequality holds, and this implies that D is a metric function on Rn.